In this video, we continue our study of numerical integration methods. In the previous video, we looked at the left point rule as well as the right point rule. And in this video, we're going to look at the trapezoid rule, which we'll see is the average of the left and the right point rules. It turns out that there are other integration methods as well, but we will not cover those in this particular course. So let's review the geometric basis of the left point, right point, and trapezoid rules. So the first two rules you've seen before, right? So the left point rule uses the areas of rectangles built on subintervals of width delta x, where the height of each rectangle is based on the height of the left endpoint of the rectangle. So what happens then is that we are using the heights y0, y1, y2, etc., up to y sub n minus 1, but notice that we're missing the data point y sub n, the height of the function at the very right endpoint of the interval at x sub n or b. So we're missing y sub n. And that's a little bit of a disadvantage because y sub n is not that difficult to calculate, or maybe we already have that value of that data point. And so it feels like we should be able to do better. If we use the right point rule, then a similar issue appears. Then what we're doing is that we're not using the value at x naught. So we're missing the data point y naught. And the trapezoid rule will fix that issue. We're actually going to be using both y naught and y sub n. But how that comes about we'll see in just a second. But the idea here is that instead of building rectangles on top of each subinterval of width delta x, we're going to be building a trapezoid instead. So in order to develop that formula, let's first of all remind ourselves how we calculate the area of a trapezoid. So I've got two trapezoids shown here already. They're exactly the same trapezoid, but we're going to look at them a little bit in a different way. So on the left, I've got a trapezoid where the width of the trapezoid is b, or base b. The left height is h1, and the right height is h2. We can dissect this trapezoid into a rectangle and a triangle, as I've shown on the right-hand side. So now, the area of this trapezoid is going to be the area of the rectangle plus the area of the triangle. So the area of the trapezoid is the area of the rectangle plus the area of the triangle. And the area of the rectangle, well, the area that has base b, and the height of that rectangle is h1, so we have b times h1. And then the area of the triangle, well, that's half times the base b times the height, and the height of that rectangle is the difference of the original height h2, but we're taking away the height h1. So it's half b times h2 minus h1. And we can simplify this. So first of all, let's multiply things out. Let's make this a half b times h2 minus a half b h1. Now we have a term with an h1 at the beginning, and we have a term with the h1 at the end. So let's combine those. We have bh1 minus a half bh1. So we're left with a half bh1 plus that original half bh2. And we can now write this in two different ways. We can say, well, that's equal to 1/2 b times h1 plus h2. Or we could write this as b times h1 plus h2 divided by 2. If we look at that last formula, we see that the area of the trapezoid is the base times the average of the two heights. The two heights h1 and h2. Okay, and that's actually why the trapezoid rule is the average of the left point rule and the right point rule. But we're actually going to use that formula that I've underlined here to develop the trapezoid rule. So we'll use this formula to develop the trapezoid rule. Okay, so let's take a look at how that would work on the next page. So here I've got a generic function, f of x, and we're going to integrate that from a to b, from x naught to x sub n. And we've divided this interval from x0 to xn in n equal subintervals of width delta x. And we're going to be building trapezoids on top of each subinterval. Okay, so the ith trapezoid, the one that I'm sketching yellow here, that area, we can use the formula from before. So that the area of that yellow trapezoid is a half times the width delta x times the sum of the two heights. Well, the height on the left is the y value at x sub I minus 1, so it's f at x sub I minus 1, plus the height on the right, that's the f at x sub I. Or if we want to use the y terminology, it would be y sub I minus 1 plus y sub I. Okay, so of course we can write down a formula for the first trapezoid as well. The area of the first trapezoid is half the base, or delta x divided by 2, times the sum of the two heights. So that would be y0 plus y1. Okay, and then a2 would be delta x divided by 2. It'd be y1 plus y2, because the second trapezoid is built on the subinterval from x1 to x2, and the two corresponding y values are y1 and y2. And you can, of course, keep going until the very end. The last trapezoid, its area is delta x divided by 2. We need to have the two heights, so it would be y sub n minus 1 plus y sub n. Okay, we're looking at the last two y values for the function on the subinterval. So at x sub n minus 1 and at x sub n. Okay, and now we need to sum up all of these areas, of course. So we've done that on the next page already. So here was the area of the first trapezoid. This one here was A1 from the previous page. The second area here is the area for the second trapezoid, and then all the way to the last one. So the last one here is A sub n. Okay. Now let's examine this a little bit, and let's take a look at what we've got. How many times do we have a y0? Well, only at the very start. How many times do we have y1? Well, y1 appears from A1 and from A2. Okay, it appears twice. Similarly, you can imagine that y2 appears twice because it comes from the second height from A2 and the first height from A3. Okay, and that keeps going. So you use twice y1, twice y2, twice y3, etc., etc. At the very end, you still have twice y sub n minus 1, and you only have 1 times y sub n. So we can group things together as we've shown on the last line. So we have delta x divided by 2. We have 1 y0. We have 2 of all of the inner data points, so 2y1, 2y2, all the way to 2y sub n minus 1. And then at the very end, we have a y sub n as well. So now you see that the trapezoid rule uses all of the data points. It puts most of the emphasis on the middle data points from y1 to y sub n minus 1, but it uses the y0 and it uses the y sub n. So this is a little bit of an advantage over the left point rule and the right point rule in that we're incorporating all of the data points that we have at our availability. All right, let's do 2 examples. The first example is the same one that we looked at in the first video as well, when we studied the left point rule and the right point rule. And that's to look at the data given to us for the SARS outbreak in Singapore in 2003. The data points that we have are spaced 14 days apart from each other. So we have 6 intervals of 14 days. That means that our delta t is 14 days. Okay, and we've been given deaths per day at each of the data points from R0. This first data point is really R at 0. The second data point is R at 14. This is R at 28. Okay, and etc., etc. And this last one would be R at 84. And we're going to call these R0, R1, R2, to R6 at the very end. Okay? So this definite integral is, of course, the total number of deaths over the 84-day period from March 1st to May 24th. Okay, and we can use the trapezoid rule to approximate that by using all of the data points that we've been provided. I've done that on the next page. Okay, so we're just using the trapezoid rule with n equal to 6. We use delta t divided by 2 times, oh, and actually I haven't used the notation R naught, R1, but we could say this is equal to R naught. This is 2 times R1, etc., etc., plus 2 times R, this is the R5, and then once R6. That would be R at 84. Okay, so that would be another way to write that formula. Once you plug in all of the numbers and put them into the calculator, you end up with 26.257, or around 26 people died during that SARS outbreak in that 84-day period. Okay, so we've used all of the data points, which is different than when we used the left point rule and the right point rule in the previous video. All right, my second example is to use the trapezoid rule to estimate the value of a definite integral for which we cannot find an antiderivative. Because we can't find the antiderivative, it isn't so easy to calculate the value of this integral, but with a numerical method we can estimate the value of that integral. So here's just a reminder of what the trapezoid rule is. We've been told to use n equal to 6. Okay, so the first thing that we need to do is we need to calculate our delta x. So our delta x is b minus a divided by 6, because we're using 6 intervals. Our b is 3, our a is 0, and we're divided by 6, so our delta x is 0.5. So now we can determine our x0, x1, x2, etc. So our x0 is equal to 0. That's our a. That's 0. Actually, let's write it down like that. It's equal to a, which is equal to 0. Our x1 is, we add delta x, so our x1 is 0.5. Our x2 is 1. Our x3 is 1.5. x4 is 2. x5 is 2.5. And x6 would be equal to 3. And now, of course, one of the things that we need to do is calculate all the corresponding y values. So y0 would be equal to sine of x0, which is 0 squared. Our y1 would be the sine of 0.5 squared, etc., etc. Now, this is easiest done with a calculator, and I've already tabulated the results on the next page. So here they are. Okay, you can easily check that work by plugging these numbers into the calculator. And now we can use the trapezoid rule to put things together. So that's already done on the next page, because all the numbers are just sitting right in front of us, right? So our our estimate by using the trapezoid rule with 6 intervals is equal to delta x. Our delta x was 0.5. And then we use all of the y values. We use the first one once, so we use 0 once. We use all of the interior data points. We use these twice. And so that one is used once. And the very last one is you use it once. Okay. Oh, and I see that it has fallen off the page here. So let's see. I need to add 0.4121 here. Once you put that into the calculator, that evaluates to 0.6415. And if we use Wolfram alpha to give us a better estimate, Wolfram alpha says that this integral is approximately equal to 0.7736. We have 0.6415, which you may think is quite far away, but actually we've only used 6 intervals, which isn't very many. If you have a computer at your disposal, you can very easily calculate the estimate of this integral using way more subintervals, using a higher value of n. So I bet that when you use n equal to 100 or 1,000 or something like that, you're going to get a number that is very, very close to what Wolfram alpha gives as well. Okay, so the higher the value of n is, in general, the better your estimate is going to be, of course, as we have seen before with the left point rule and the right point rule. All right, well, that's it. So we've looked at 3 numerical integration methods to estimate the value of a definite integral. We've tried the left point rule, the right point rule. The disadvantage of those first 2 rules is that one of the data points is left out. For the left point rule, you leave out the last one. For the right point rule, you leave out the first one. The benefit of the trapezoid rule is that you use all of the data points. You put most of the emphasis on the middle ones, and you put a little bit of emphasis on the end ones, but you do use all of those data points. Now, as we said before, there are other numerical integration methods as well, but those are not covered in this particular course.